Hi, everybody. We're going to start talking about Chapter 55 here. It is the part of Chapter 55 dealing with carbon cycling. And what we're basically discussing is many of the things that we went over in class, such as the continued availability of carbon in ecosystems depends on carbon cycling and the carbon cycle, the thing that we went through. Okay, so this should be a good review for you. So when we were talking in the last section, we took a look at nutrient cycling. We took a look at the nitrogen cycle. You might have learned about the water cycle in an earlier class, and then of course we went through carbon cycles. And you have to keep in mind that there's certain reservoirs for the elements. For instance, with the nitrogen cycle, the atmosphere is a major reservoir. Living organisms are, the soil is, etc. So the process that transfers the elements between the reservoirs is what you want to concentrate on when we're talking about the nutrient cycling. So each reservoir has two questions that you need to answer. Is there an organic or an inorganic type of material that it belongs to? And are the materials directly available for use by organisms? So for instance, like with the carbon cycle, when they're locked up in rocks, they're not necessarily available for use for organisms. So you have to kind of go through and see some of the processes. Like for instance, when we look here, you can see that fossilization, like in the formation of fossil fuels, gives us some coal and peat. We went over that in class. I'm going to go over it again here in a little bit. Burning those fossil fuels here can return the inorganic forms, like for instance CO2, into the atmosphere where the autotrophs can use it. If they're locked up in the atmosphere or in the soil, in the water, things like that, you can have these things, especially if they're in the soil and or in the water. They can go and become minerals and rocks. They can be unavailable as nutrients, so forth. You can get those out through the process of weathering sometimes. That weathering here is going to return it back to the atmosphere, for instance, with like acid rain, bubbling the CO2 off of certain rocks, things like that can do it. And then just assimilating them things out of the atmosphere, for instance, in the form of or in the process of photosynthesis, can get these things into living organisms. So you can just kind of see how the nutrients get cycled through the reservoir using, for instance, carbon as an example right there. Okay, so carbon's important because it's the framework. It's that compound that can form four bonds. For instance, you probably remember you have carbon, and then you've got the four valence electrons here, and it's the basis for all of the biomolecules. So that's why it's such an important thing, and just keeping in mind how these things cycle through. Photosynthesis takes that inorganic form of carbon in CO2 and converts it into forms that heterotrophs can use to take up, and that's just a small part of the carbon cycle, things that we were talking about. So it's found in great proportions in fossil fuels, of course. It's found in the sediments of aquatic ecosystems as the organisms die and fall to the bottom. The oceans obviously can hold a lot of carbon in some of the various forms that we talked about. Calcium carbonate in seashells, the hydrogen carbonate, etc. Plants and animals hold a lot of the biomass and so forth. So if you look here through some of the reservoirs, you can see the oceans hold a ton of carbon, and they can continue to hold the carbon, and the animals that are in there, the plankton, the little mollusks, all sorts of different types of organisms that are dwelling, things we've discussed in class, can really take them up. Rocks and sediments, of course, have a lot of carbon in this as well. And then just looking at some of the other things that are in there that we've discussed in class, especially with the fossil fuels and so forth. Okay. So we said that aquatic ecosystems can take up carbon in the form of dissolved carbon dioxide, and I think we looked at this picture in class, and we're just kind of discussing how carbonic acid is formed in the oceans, and that can contribute to some of the acidification of the ocean. And how that can affect the living organisms. So just kind of consult the pictures that you draw and some of the notes that perhaps you took when we were discussing these things, and how the ocean can serve as a reservoir, and some other bodies of water can too. And we discussed some of the ways that we can kind of measure this with the flask with the phenolphthalein in it, making it slightly basic so it was just faint pink. And then if we come back the next day, we know that it's absorbed a lot of carbon dioxide, so it's become a little bit acidic, and then the solution might be clear again. So that was one of the things also that we discussed. Okay, so the largest reservoir of carbon is found in sedimentary rocks like limestone, and we just saw that in the graphic a couple minutes ago. And here's the White Cliffs of Dover, and if we look, we can see this is another kind of angle that we're looking at. And then just across the sea here, you can see we've got another formation of a lot of the limestone. And just to give you an idea of the size here, these are some people down there, probably having a picnic or something. And, so the just the sheer magnitude of the amount of carbon that's locked up there. And there's another kind of picture, at low tide, so you can see kind of the angle. And these are just ancient seabeds that were uplifted when the continents were moving and things like that. So animals like reef-building corals, mollusks, anything that has the hard part made out of calcium carbonate, these are the things that can absorb the carbon out of the water. And then when they die, they sink to the bottom. And you can see here the shells of this marine organism. It's kind of locked in this sandstone here, and these things get fossilized. So that's a reservoir of carbon in the form of calcium carbonate. And some of the key processes of the carbon cycle is just the conversion into carbohydrates by autotrophs. So we discussed this, that's photosynthesis. And then, of course, the return of that carbon dioxide into the atmosphere through the process of cellular respiration, which many living organisms perform. And when the CO2 gets produced by the heterotrophs, it diffuses out, whether it's a terrestrial organism or an aquatic organism, just it's diffusing out through the process of exhaling. And in this case with the fish, it's diffusing out as the fish kind of move their gills and move the water over. It's very similar to the action of breathing, so you're getting the exchange of the gases. So the water that has more oxygen in it than the blood, the oxygen is going to diffuse in, and vice versa. The carbon dioxide being more in the blood is going to diffuse out, and you get that gas exchange, okay? In the plants, you have this diffusion of gases in the leaves. So in other words, the CO2 can diffuse out of the autotroph and then into the atmosphere, into the water, if it's an aquatic plant, something to that effect, okay? All right, so we gave some of the examples of the ways in which we can get a lot of carbon into the atmosphere over geological time. So we talked about volcanoes. Those have a definite ability to do so. But one of the things that we're doing, of late, since really the start of the Industrial Revolution, is burning fossil fuels. And this is adding a lot of carbon dioxide. We're taking it out of these reservoirs and getting it into the atmosphere much quicker than we're removing it. So methane is another gas that's produced in organic matter in anaerobic types of conditions. You have methanogens, archaeans. These types of organisms are able to survive in these anaerobic environments, and they produce methane as kind of a byproduct. And there's some man-made or anthropogenic sources, though, of methane, as well as the natural sources, some of which we were just talking about. So during the process of the formation of methane, such as in swamp gas or in the sediments of swamp that we see right here, as this organic matter is being decomposed in an anaerobic condition, we get the formation of methane. And some of the methane can kind of bubble out of the solution. So if you've ever been, to a lake or a swamp or something like that and kind of agitated the bottom, you see a lot of bubbles coming up, and some of that is definitely methane. And some of it gets trapped in the ground, some of it's released occasionally, and some of it's released on a pretty kind of regular basis. So the natural sources, some of which we listed in class, natural sources of methane, swamps, ruminant types of animals, wet soils where the decay is occurring in an anaerobic type of an environment where these methanogens are working on it, and then some anthropogenic or some man-made sources are rice paddies, landfills, sewage treatment plants, factory farms, those types of things where we're going to produce a lot of the methane. And methane is an important greenhouse gas because of its potency. It's about 21 times the amount of greenhouse kind of effect as compared to CO2. So methane is an important thing that we really want to try to limit as much as we can. And it can be removed from the atmosphere, but it's pretty slow. And you have just, the natural process here. You can see the methane interacting with these oxygen molecules to give us some carbon dioxide and some water. So when it's being broken down, it's producing another greenhouse gas in the form of CO2. So the methane removal from the soil comes from these methanotrophs. There's organisms that can kind of use methane as an energy source and pull it out of the ground that way. And some microorganisms, these methanotrophs, they're going to use it as a fuel source, kind of like we use glucose as a fuel source. And there's a complex pathway that's going to break it down. They're going to respire and produce CO2 and water, much like we do when we burn the glucose molecules. All right, so the next thing we're going to discuss here is the peat formation, and we went over this in class, and again, this should serve as a good review for you. And when plant material starts to decay in these anaerobic types of conditions where the environment becomes acidic, you get a preservation of these things. They don't rot as much. When they get buried, they can start forming these types of fossil fuels that we discussed. And a lot of the vegetation around these types of environments, these peat bogs and so forth, are usually mosses, and we all know what those are. Some shrubs, and then sedges are just like tufts of grass, more or less. Okay. And when the soil becomes waterlogged, it usually becomes acidic and anaerobic, and this contributes a lot to the formation of peat because you don't have that breakdown. And we know, again, if you remember Tullen Man and looking at the skin of that person who was buried in a peat bog and then discovered, I don't know, a couple thousand years later, you could still see pretty much the pores on their skin because the decay process had been broken down so much. And that's essentially what's happening with peat. And peat formation is the first kind of step in the production of coal, because this stuff isn't breaking down, it's just getting compressed when we're forming the coal. So if we look here, you can see that as the kind of glaciers recede, you've got these cool, wet conditions, and oftentimes the body of water is kind of underlain by a layer of clay, which makes it kind of impermeable, so it's going to hold that water. And then you get the formation of these plants around the water source. And now these things, as they begin to kind of rot in this water from the standpoint of, or break down in the water, they start to get buried more and more. But the breakdown is very, very slow. And what happens is the waters become acidic, and then the breakdown is even slower. And now you get the kind of accumulation of these, leaves, mosses, pine needles, etc. These things start to kind of accumulate. And then the water, basically, because it's accumulating, the water doesn't have any place to go, so it's starting to run off. And now you've got kind of this thick mat now, which is mostly peat, and the lake is pretty much filled in by this point. And now things start to grow over the top of it, and now you're getting this kind of peat bog formed down here, as you can see. So all of these things started to grow. Again, it's kind of a cooler area. You've got lots of pine trees. You've got lots of different types of organisms kind of growing over the top of it, and you get this dome formed. And now the organic material starts to continue to build up, and eventually it's going to get, through, thousands of years, it's going to get buried, and then you can either harvest it. There's a lot of places in the world where there's peat bogs. They harvest this for fuel. They can dry it out and they can burn it. So you can use it in your garden to kind of hold water, condition the soil, slow breakdown, as you're starting to add aerobic conditions to it, different types of bacteria are making these nutrients available. So it's a nutrient-rich source as well. But if it continues to get buried over time, over the course of millions of years, now you're starting to kind of get this heat, this pressure kind of applied to it, and that's what's going to contribute to the formation of coal. And then, I went a little bit further. You underneath this kind of sedimentary rock here down by step 4 here, you can see you're starting to get a lot of time. You're getting a lot of accumulation as it goes through here, and as this sediment is kind of on top of the what was formerly the peat, you get more accumulation of stuff, and eventually that peat with the heat and the pressure is going to become the different types of coal that we talked about in class, from the lignite to the bituminous coal to the anthracite. So those are the different types of things that are happening. And really, when you're thinking of coal, a lot of times you're thinking of this anthracite, this really hard rock, this energy dense type of material that gets burned. That's taken millions of years to formed under very high pressure from formerly living types of organisms. Okay. Now, as the formation of oil goes, millions of years ago, about 360 to 300 million years ago during the Carboniferous period, there's lots of plants and animals living all throughout the world, especially in the ocean, and they absorbed a lot of the energy from the sun. Photosynthesis was taking place, and a lot of this energy was formed in their bodies, whether it's a plant or an animal, and it was a huge source of carbon. once these animals began to die, their bodies sank to the bottom. And once they were, at the bottom of the ocean, the accumulation of the sediment, you started to get lots and lots of heat and pressure started to form. So you've got these accumulations of sediment, these deposits at the bottom, but they're continually being buried further and further by the organisms that are dying above them. And as the layers of sediment started to increase, so too did the heat and the pressure. And this heat and pressure started to really cause a change in the types of materials that were there. And the amount of heat, the amount of pressure, the type of biomass that you had, all of these things are going to kind of contribute to whether or not you're getting oil or some sort of a natural gas being formed. Okay? And as the heat were to increase, you get a lighter and lighter gas being formed. But if the temperature gets even higher now, the biomass, if it's predominantly plant material and or you have a really high heat, this is where you're going to get natural gas type to form. So it's the things that we would burn, in our houses to keep warm, generate electricity, to boil the water, turn the turbine, generate steam, that sort of a thing. So that's what we mean by the natural gas. And now, after the oil gets formed, it travels from the source rocks through the pores, the cracks in the rocks, etc. And then some of it might eventually reach the surface, and others kind of get trapped in these kind of rocky formations, these domes that are impermeable. And that's where we can kind of drill into them and get the oil, the natural gas, or both out of them. Okay, some of the reservoirs that are there, some of them are on the land, such as in Los Angeles. If you go to the Rancho La Brea and the La Brea tar pits, that's right there on the surface. And there's other places in the world where that's also the case. And then others are buried miles deep in the Earth's crust. And so and aside from that, even buried deep in the Earth's crust, deep beneath the ocean. So there's all sorts of places, of course, where we find these fossil fuels. And the majority of the reservoirs consist of oil, gas, and then some water. And based on their density, these things are normally, separated out, and the less dense stuff is on the top, and then, like the natural gas, for instance, and then you'll have a layer of oil, and then below that is the water. So the less dense stuff rises up. We get that stuff out, and that's what makes up, crude oil that we're going to then refine and get gasoline and kerosene and diesel fuel and all of those types of things. Okay, so 70% of the deposits that were formed during the Mesozoic, or that kind of middle life age, and then 20% were formed during the Cenozoic, which is the more recent time, and then 10% was formed during the Paleozoic, or a long time ago, the old age, the old living organisms. And the differences are the results of many different types of factors. So you've got the Mesozoic, where the climate was very tropical, and you have a lot of plankton, a lot of ocean-dwelling organisms, and these things, once they sank to the bottom, they encountered these hypoxic types of conditions. You had this stagnation, and there wasn't a lot of breakdown. So you have a lot of organic rich types of deposits that are there, and these things are the things that form like kerogen, and they give rise to the different types of fuels that we can get out. So now the burning of these fossil fuels, of course, releases large amounts of CO2 into the atmosphere, and this is kind of entering now, going from the fossil fuel state, the organic rich state, to the inorganic carbon dioxide kind of portion of the cycle in the atmosphere, or perhaps being dissolved in the oceans and things like that. And of course, now we're currently taking out far more energy from the reservoirs and putting it into the atmosphere in the form of CO2 than is being taken out by the plants. Okay, so there's a little video here that I want to watch now, and get this thing pulled in here. Go over here. Sorry. There we go.
Our cars, buses and planes, powers our electricity, and allows us to cook our food and heat our water. Most of today's energy needs are met by fossil fuels like coal, oil and gas. These unique, high-energy fuels are non-renewable resources that took millions of years to form. About 2 billion years ago, marine organisms like algae and microscopic animals and plants died and settled on the ocean floor. Beneath other sediments in the ocean, and in the absence of oxygen, these fossils changed into a substance called kerogen. Under heat and pressure, kerogen gradually changes into oil or gas. The whole process usually takes at least 1,000,000 years. At the molecular level, oil and gas are hydrocarbons made up of hydrogen and carbon atoms. The constant pressure and movement of the Earth's crust squeezes oil and gas through the pores or spaces within rocks. Some oil and gas reaches the Earth's surface and seeps out naturally into land or water. Often it is trapped beneath the surface by impermeable layers or rock structures, like faults and folds. Within the crust, oil or gas deposits build up and form reservoirs. Reservoirs are like vast sponges filled with oil and gas. They can be as large as a city. To find oil and gas deposits, geologists use a number of different survey techniques, including seismic surveys, gravitational surveys, and geological mapping. Seismic surveys use reflected sound waves to produce a 3D view of the Earth's interior. New technologies, such as four-dimensional projections and sophisticated graphic renderings of rock structures, are improving the way we find conventional oil and gas deposits. Energy resources that are currently difficult or expensive to extract are called unconventional oil and gas. In a world with limited energy resources, people are looking at more efficient ways of tapping into unconventional oil and gas, or at alternative and renewable sources of energy from biofuels or the sun. What do you think will be the energy sources of the future?
All right. I hope you found that useful, and we'll see you in class.